Swayam Prabha. Digital India. Educated India.
Welcome. So we are discussing finite element method for Timoshenko beam. So in the last three lecture we have discussed basically the theory and its finite element formulation. So in this lecture we will just do a simple problem to understand what is these different procedure means. So let us first recap what we have done. So first thing, first what we have done is that we understood the theory of Timoshenko beam, which is governed by this equation, that is dw dx plus theta equals to qx or q0, whatever you take. And there is another equation, so ddx of the bending term, that is d theta dx, and minus your ksga into dw dx plus theta. So this is equals to 0. And the boundary condition, that is we all know, that is ksga into dw d theta dx plus theta, or w has to be given, and ei d theta dx, that is moment or slope, has to be given. So look carefully that these two equations we have done its weak form, and then we did two interpolations. So where we briefly introduced the shear locking, the problem of interpolating with the same degree of polynomial w and theta. So that leads to an inconsistent formulation, because w and theta in a thin beam limit should be almost equal, because it will follow the Euler-Bernoulli beam theory. Now, so in this connection we have understood two methodologies or two type of element, even though the stiffness matrix for both these procedure comes to be equal. The only difference is the force vector. So basically consistent interpolation of dw dx and theta. So this is one formulation, and another one is, which is the main problem of to alleviate numerically the numerical locking or the shear locking we discussed. So that is the reduced integration method. So reduced integration method. So now you see the boundary conditions here are a little bit different than the Euler-Bernoulli beam theory, because here we have the shear deformation, that is the shear strain is non-zero essentially. So Ks is the shear correction factor, which is to account for the parabolic distribution of the shear force, so, or the shear stress essentially. So now there are four boundary conditions here. So this 4 boundary condition is not due to the fourth order differential equation. One has to carefully look at these differential equation. These equations are second order equations. So, there are two differential equations, and there are highest derivative present in the differential equation is of order 2. So, that is why there are 4 boundary conditions required. On the contrary, the Euler-Bernoulli beam theory, you need 4 boundary condition because of the fourth order differentiation exists, which is ei d to the power 4 w by dx to the power 4 equals to q. So, that is the basic difference, and similarly in the finite element formulation we can do with the Lagrange interpolation, because in case of a Euler-Bernoulli beam theory we had to do with the Hermite interpolation because of the continuity of the dw dx, because dw dx, even though it's a in case of Euler-Bernoulli beam it is equals to theta, that is slope is actually the derivative of the displacement. So, in order to be consistent with the slope, we need to have a derivative continuity in the interpolation. So, that is the requirement for Euler-Bernoulli beam theory. Now, in doing this, the stiffness matrix we also derived, which is essentially the stiffness matrix of a Timoshenko beam, which is something like this, that is G A K S by 4L. So, here essentially I am just taken 4L, I have just this 4 I have just make it so that I can write it properly. So, 4 minus 2L minus 4 minus 2L, and then you have L square plus alpha 4 no, that is 2L and then L square minus alpha, then this is also 4, then 2L L square plus alpha. So, now here alpha is essentially your I redefined this alpha, so which is 4 EI by. So, earlier I was defining EI by kappa SGA, now I just added 4, so that the form looks little simple to handle. Now, in the consistent interpolation we did this. So, there is a essentially there are 3 nodes, but in these 3 nodes there are only displacement nodes are essentially at 3, that is the quadratic interpolation, and while the slopes are only at the end node. So, this is how we did for this thing. So, these are displacement, these are rotations. So, these are rotation interpolation. So, that is slope interpolation. So, that is theta. Now, theta also linearly interpolated, and these 3 are displacement interpolations. So, in case of reduced integration method we use 2 noded beam element. So, that is consistent interpolation element, and this is reduced integration element. So, now here we did for slope and displacement with the same number of nodes, and we can use the similar interpolation function for displacement as well as the slope. So, this is actually the reduced integration method. Now, in order to just find out how these elements, the finite element procedure, essentially let us do a simple problem where let us consider a simple beam. So, this problem is very much simple. So, so this is, we all know this kind of problem from our B take itself. So this is the length L and this is also length L. So now here this, let us take Q0 as constant. So now in order to find out the deflection of this beam, we can either use the Euler-Bernoulli beam theory or Timoshenko beam theory. So let us assume that we have three node and two element, that is element 1 and element 2. So element 2 is free from the external loading, element 1 is having only UDL. So from the Euler-Bernoulli beam element, you can if you do solve this problem, the results that will come, that is W2 is essentially Q0 L to the power 4 divided by 48 EI, and W1 is theta 2, that is the slope at this point, that is midpoint of the beam, is actually Q0 L cube by 96 EI. Now what happens if I solve it by the Timoshenko beam theory? In case of a Timoshenko beam theory, the procedure is very much similar to Euler-Bernoulli beam, only the stiffness matrix will be different. Now let us find out the Timoshenko beam theory, what will happen to the stiffness matrix. So this is my Timoshenko element, the same way that I did, that is W1 theta 1, W2 theta 2 and W3 theta 3. So first let us do the reduced integration element, that is the B. So reduced integration element, so there are two elements, so I can just if I take EI and GA and kappa S or KS, that is shear correspondence factor constant over the beam, then it is just addition of two elements. So GAA KS by 4L, then we will have this bigger matrix equation, which is 4. So this is symmetric. So 4 minus 2L minus 4 minus 2L, that is L square plus alpha, this will be 2L, then L square minus alpha, then this will be 0 0 and this will be also 0 0. Well, in the third element there will be 4 plus 4, that is coming from second element, then this will be again your first element will come 2L, then from the second element is minus 2L, then this will be 0 0 and then this term will be 4, that is no, not 4, that is L square plus alpha, and also L square plus alpha. So that is 2L square plus alpha, then this will be sorry, this will not be 0 0 because these terms will be there. So 4 minus 2L, that will be minus 4 minus 2L, and then another term, that is let me write it properly, that is L square plus alpha plus L square plus alpha, just to highlight the white from second element. So this is, and then 2L will be there, then L square minus alpha will be there, and then the third element, that is fifth and sixth degrees of freedom, that is W3 and theta 3. So that will be 4, then 2L, and this is L square plus alpha. So this is my whole assembly, or the whole stiffness matrix, which is a 6 by 6 stiffness matrix, and this matrix is essentially symmetric because this is a symmetric matrix. So now what will be the degrees of freedom? Degrees of freedom will be W1 theta 1, W2 theta 2 and W3 theta 3. So this will be my degrees of freedom. Now there will be a force vector, associated force vector. So, for the first element we will have only the UDL. So, UDL will have only two components. So, there will be, this is only the UDL term. So, this is Q0 L by 2 if this is the Q0, then the shear force means the force will be Q0 L by 2, that is L by 2, and this is also Q0 L by 2. So, now this will look like this, Q0 L by 2. So, here there is no this moment and anything. So, that is why this is 1, then this will be 0, then this will also be 1, this will be 0, then 0, then 0 and 0. So, this is this, and then there will be another term that will come from the boundary condition, which is actually Q11, Q12, Q13, Q14, then Q1, Q2. This is contribution from second element. So, Q21. This will be coming here. So, this will be Q11, Q21 plus Q2 2, then Q23, Q24. So, this is essentially the this boundary condition term. Now, we have already for this beam we know the boundary condition, that is slope and deflection at the node 1 and node 3 is essentially 0. So, which leads to this quantity must be 0, this quantity is given. So, since it is given, then we can say that is this quantity is 0, this quantity is 0, and also there is no the moments and the shear force at the fixed end is unknown. So, this is not equals to 0, not necessarily 0, this is not equals to 0, but at the midpoint there is no support. So, this quantity must go to 0 and this quantity must go to 0. So, naturally my reduced stiffness matrix will contain, since the homogeneous boundary condition. So, reduced stiffness matrix only contains this block. So, this block will matter and obviously this will be there. So, these two terms will be there and these two terms are essentially 0. So, finally, if I write my equation, that is this looks like this, that is GAKS by 4L, and then this will be my the matrix, that is your 2 by 2 matrix, that is 8, 0 and then 0 to L square plus alpha, and then you will have only W2 and theta 2, and obviously you will have Q0 L by 2. So, Q0 L by 2 will be there, and this is 1 and 0. So, 1 and 0. So, now if you look these two equation, if you solve these two equation, then you will get the W2 and theta 2 from Timoshenko beam theory. Now, if you solve this equation, this looks like Q0 L square by 4 Q0 L square by 4 G, A and Ks. Now, interestingly, if you see that theta 2 is essentially 0. Now, if you look the Euler-Bernoulli beam theory solution, which is no way correct, that because this solution, that is theta 2 is 0, essentially is no way correct. but you can try and improve the solution if you just do the if you take the number of element, higher number of element, or if you increase the number of element, this solution will approach to this solution. Now if I just to check whether this is correct or not. So, let us say that Poisson's ratio is 0.25. So, let us say Poisson's ratio is 0.25, and then the shear modulus, that is G equals to E by 2 into 1 plus nu. So, that is E by 2.5, so which is 2 by 5 E, right, and kappa S, that is shear correction factor, let us take 5 by 6. Then this term, this 4, okay, we need A also. A is actually B into H, that is B is the width of the beam and H is the depth of the beam. So, that is B, let us say B H cube by 12 into 12 by H square. So, I can write this is as 12I by H. So, I just wanted to this displacement, how it is correct, how much correct it is, to find out that. So, 12I by H. Now, this term, that is this term, if I now write it, that is 4GA kappa S, that is equals to 4G is actually 2 by 5 E, and then A is 12 I by sorry, this is H square, 12I by H square, and then kappa S is 5 by 6. So, if I cancels this, then this will look like this is 2. So, this is 16 EI by H square, 16 EI by H square. Now, what I will get is that my W2 is essentially Q0L square by 4GAKs. That looks like my Q0L square H square by 16 EI. You see, this contains L, the length of the beam, as well as it contains the thickness of the beam. So, I can just represent this thing like this. So, that is 16 EI, and this I can write H by L whole square. So, this depth to thickness ratio, depth to length ratio is vital for Timoshenko beam theory. So, naturally this will not be equal to the Euler-Bernoulli beam if this ratio plays an important role. Now, I will come back to this accuracy of this theory in the finite element method probably in the next lecture, but let us see if I now want the consistent interpolation, for instance the consistent interpolation or the CIE, that is theory. This if I do, that stiffness matrix will remain same. So, stiffness matrix won't have any changes, only changes will have the force vector. If you remember that we condense the equation, and the stiffness matrix equation looks like this, that is Ke for this, and then this is actually W1, W2 and theta 1 and theta 2 like this we did, and then this is actually F1 plus half of F3 hat, then this is also F2 plus half of F3 hat, and this is actually 1 by 8 Q, sorry, this is F3 hat h square, and then this is 1 by 8 f3 hat h square. Now this plus, actually you have, this is from q1 or this is element, so q1 q3, so this is a displacement node, you see, and then this is q2 and then q4. So that's what we derived during our theory derivation. Now here, that is f3 hat is essentially your f3 plus q hat, which is, that means the displacement nodes will have 3 nodes, that is 1, 2 and there is a 3. So now this UDL I have to distribute over this, so 3. Now this f3 hat is essentially f3. How can I find out? Because this f1, this is f1 essentially, and this is f2 and this is f3. Now if this is a quadratic, this is a constant loading. Now if I just use the quadratic interpolation, then my force vector will be essentially phi I q0. So if you remember that force vector, how we calculated the force vector, that is 0 to L, that is phi I of x and then q0 dx. Now here this is my quadratic shape function. So this is my quadratic shape functions. Because if you have seen for the consistent element, this is a quadratic shape function. So my f1, f2 and f3 I have to find out accordingly. So which I can essentially, we can write it. I have done this earlier probably. So which I can write it in this manner, how it looks like. So that is your f1 is essentially q0 L by 6, or let me write it here. So if you just put the quadratic Lagrange shape functions and q0, then f1 will look like q0 L by 6, and this is 4 by 6 q0 L, and this is also q0 L by 6. Now in the beam element is essentially this beam element, this beam, there is no force acting on this. So naturally at the midpoint also there will be no thing. So this quantity will be 0. So now we can find out the force vector. So the force vector, now if I just rewrite this equation and say this is my Ke, and let me write it in a little bit different way. So this is my, so see, this Ke and this Ke is not same. I am just shifting the rows. Essentially I want to be consistent with the previous formulation. So essentially this will go here and this will go here. So accordingly my force vector will also change. This will go here and this will go here, and similarly this will come here and this will come here. Sorry, this will go here. So now this Ki, let us say this is bar. So this is now consistent with this Ki, because I have to shift the row and columns accordingly. So it is just row and column shifting of the stiffness matrix. So now this stiffness matrix is equals to the reduced stiffness matrix, reduced integration element, which we derived earlier. So now W1 theta 1 form, we let me write it, W2 and theta 2, and then what I will have is essentially this. So let me derive for the first element. So that is your QF1 is essentially your so this term, let me write it. So F1 plus half of F3 hat, then minus 1 by 8 f3 hat h square, then this is f2 plus half of f3 hat, and then 1 by 8 f3 hat h square. Now this is just rearrangement, and then your q1, q1, q2, q3 and q4. This is the way we represent. Now the first term in the force vector, or first element in the force vector, we can compute. That is, f1 is essentially your f1 plus half of q, f3 hat is essentially f1 plus half of f3. So f3 is your this equation. So f3 is this plus q prime, so or q hat. So q hat is 0. So now f1 is essentially q0 L by 6 plus half of f3, that is your 4q0 L by 6. So this is 2. So this is q0 L by 6, q0 L by 2. So now if you solve this thing, and then similarly 1 by 8, that is 1 by 8 f3 hat h square is also can be calculated. 1 by 8 f3 hat is essentially your f3 plus q hat, that is your 1 into h square, then that will equals to 1 by 8 f3 is your q0 L by 4q0 L by 6. So that is into 4q0 L by 6 8. This is not h, this is L squared. So we are denoting length as L. So now this will be L square. So now okay, so I have represented in terms of h because I have taken it from Professor Reddy's book. So this is L squared, this is L squared. So now this is this. So now this is also L squared. So this is also L squared. So if you see, this is 2. So 1 by 12 q0 L cube. So if 3 is this q0, I think I'm doing some mistake here. If 3 is, yeah, so I think it will be q0 L squared by 12. So if 3 is actually 4 by 6 ql. So and this is actually half of q3L, I think. Okay, so then it will be q0L squared by L squared. I think this is q0, not L squared. This is q0L. Okay, so we have derived it earlier. So let us don't derive it now. This will be L. So now this will looks like q0L squared by 12. Now this will give me the total force vector, which is my now this equation will look like f1 plus half of f3 hat minus 1 by 8 f3 hat L, and then this will be my f2 plus half of f3 hat, then 1 by 8 f3 hat L. So this will look like this. So Q0 by L into 2, and then this is minus 1 by 2 Q0 L squared by Q0 L squared, then this is Q0 L by 2, and then this will be a positive moment, so that is half of Q0 L squared. So this is my force vector. Now if you look carefully, our stiffness matrix becomes same. So that is my GAKS by 4. So obviously the reduced stiffness matrix, and then I will have the other formulation is very similar, because which is the other formulation is very means the CIE formulation is very similar to this. That is, this will be same as this, because this will be 0 and other 2 degrees of freedom is 0. So just reduced stiffness matrix, the form won't change. So that is the case. Now here what I will have is that 8 the form will be same, 8 0 and 0 2 into L square plus alpha. So now this is actually W2 theta 2 is essentially what will have Q0 L by 12, that is equals to 6 by 6 by 6 by L. Okay, so that's what we'll get. Now solving these two equations, I will again get W2 and W3, and W2 is same as what we get by the consistent, by the reduced integration element, that is 4 KSGA. So this again we can write it as with the new 0.25, and then A is 12 by 12 I by H squared, and then your G is 2 by 5 E, and then yeah, that's all. So if you do this, then what you are getting is QL to the power 4 by 16 EI into small h, that is the depth of the beam, and this is L by whole square. And theta 2, which was earlier 0, what theta 2 will get is essentially Q0 L cube divided by your 6 into kappa S G A L square plus 4EI. So you see that the expression is not simple. While the Euler-Bernoulli beam, from the Euler-Bernoulli beam theory, you will get Q0 L cube by 96 EI. Now in the next class, actually I will try to show some of the thing in this some of the results that will establish the finite element formulation more detail. So essentially this also we can transfer it to by substituting this, we can also simplify this, that is Q0 L cube by 24 EI. So that into essentially 1 plus H by L whole square. Okay, so that is to the power minus 1. Okay, so that is actually the you can do this by substituting this. Now here what in this problem we just saw how to do that stiffness matrix how to do it with the different element. That is your CIE, that is consistent interpolation, and the your reduced integration element, that is where we just use the same interpolation. Now it was found that this consistent interpolation or the reduced integration element, we can use the higher order element. So in the higher order element also we can, for instance, in the reduced integration element, what we are interpolating is W as my W1 theta 1, W1 phi 1, that is W1 phi 1 plus W2 phi 2, and for theta is actually theta 1 phi 1 and plus theta 2 phi 2. Now here phi 1 and phi 2 are linear polynomials, so 1 minus x by L and phi 2 is x by L. So here also I can use quadratic polynomial, for instance the quadratic Lagrange polynomial that we have used. So in that case this is a linear reduced order element, so we can use a quadratic means quadratic reduced order element. So quadratic reduced order element. So that is, it will be 3 node, but same number of displacement as well as slope nodes, but shape functions will be quadratic. So likewise we did for quadratic bar element. So W1 phi 1 and so on. So W1 phi 1 plus W2 phi 2 and W2 phi 3. So we will see that this element has little better performance because of the quadratic nature of the polynomial. So that is theta 1 phi 1 and theta 2 phi 2 and theta 3 phi 3. Similarly, that CIE also we can use linear as well as, so in CIE is kind of mixed kind of this thing, because your slope is essentially you are interpolating with the linear polynomial, while the displacement you are using quadratic polynomial. We can do the same thing. For instance, slope we can do the quadratic thing, and displacement we can do the cubic thing. So in the next class we will solve another problem and see the effectiveness of this formulation. So I stop here. Thank you.